Dear ladies and gentlemen, we would like to express our gratitude to the conference organizers for providing us with the opportunity to present our research on the parallel optimization of generation capacity structure in a local grid under military threats. This work holds particular significance today because ensuring energy security has become increasingly crucial in the face of military attacks specifically targeting energy infrastructure. Here is an overview of today's presentation. We will start by discussing the motivation behind our research, focusing on the need for energy security in crisis scenarios. Then we will review the state-of-the-art approaches like Bender's decomposition and black box algorithms, and introduce the objective of our research, constructing efficient solvers for optimizing generation capacities in a local grid. Next, we'll dive into the mathematical model we used, followed by the detailed explanation of the decomposition and parallelization algorithms. After that, we'll compare the performance of different solvers in terms of speed and reliability. Finally, we'll walk through a case study and conclude with the key insights from our work and discuss potential future research directions. Our motivation for research in generation capacity optimization arises from the urgent need for high reliability and resilience in power systems, especially in crisis scenarios such as military and terrorist attacks. Renewable energy sources and energy storage systems are crucial in this context, as their geographical distribution allows generating units to remain operational even if certain nodes are compromised. However, planning the capacity of such systems is computationally intensive and time-consuming, as these tests are often formulated as large-scale mixed-integer linear programming problems. One approach to address the computational complexity of large-scale mixed-integer linear programming problems is Bender's decomposition. This method breaks the problem into a master subproblem and secondary subproblems, working iteratively by solving subproblems and adding new constraints to the master subproblem at each iteration. However, it has its limitations, including a large number of iterations and a rapidly growing set of constraints which may lead to high memory consumptions. Another approach involves using derivative-free optimization methods, where the system is treated as black box. Techniques like genetic algorithms and colony optimization and particle swarm optimization fall into this category. These methods are particularly useful when the mathematical formulation of the objective function is not available. However, the performance of this algorithm can vary significantly depending on the specific characteristic of the problem being solved. The goal of this study is to develop mixed-integer linear programming solvers that can efficiently solve the problem of optimizing generation capacities in a local grid while minimizing computational resource consumption. Given the complexity of these optimization problems, effective solutions can only be achieved through the use of high-performance parallel computing. This made the research and development of parallel methods and algorithms for optimizing the structure of generation capacities in a local grid an extremely relevant and timely task. The mathematical model we use represents a typical local grid with renewable energy sources and energy storage units. It includes parameters such as capital and operational cost per watt, weekly electricity consumption profiles, and capacity utilization profiles for wind and solar power plant. The model variables include the number of generating units, the weekly load profiles for renewable energy sources, the energy stored in storage units, and decisions regarding electricity purchasing and selling. The model also incorporates constraints such as balancing electricity productions and consumptions, along with various technological restrictions. For instance, the charging and discharging rates of energy storage systems are constrained by their physical characteristics. Additionally, the ability to buy or sell electricity on the wholesale market is limited by the maximum load capacity on transmission lines. The ultimate objective is to minimize overall costs while ensuring system reliability. To manage the complexity of optimizing the structure of generation capacities in a local grid, we use a decomposition approach that splits the problem into a first stage master subproblem and several second stage subproblems. The master subproblem addresses decisions related to investment costs, such as the number of generating units to build, while the subproblems focus on operational costs and technological constraints. This separation enables us to solve the subproblems independently and in parallel, while the others in parallel with the others, significantly improving efficiently. Our parallelization strategy is designed to maximize efficiently at multiple levels. For the master subproblem, we use a population-based algorithm which generates several candidate solutions at once. The objective function for each of these candidates is then evaluated in parallel, speeding up the process of finding potential solutions. Additionally, the second stage subproblems focused on operational costs and constraints are also solved in parallel using general-purpose solvers. This two-level parallelization approach ensures that both the master and subproblems are processed simultaneously, leading to faster and more efficient optimization. In developing our solvers using the problem decomposition and two-level parallelization approach, we employed different underlying solvers. For the master problem, we use meta-heuristics, which includes the evolutionary centers algorithm, and MIDACO, which is based on end colony optimization. For the secondary problems, we relied on SKIP, a well-known solver for mixed integer programming. This combination of solvers allows us to effectively tackle both the investment and operational aspects of the generation capacity optimization problem. Here, we compare the time it takes for each solver to find a solution. The SKIP solver running on a single CPU thread served as our benchmark for comparison. Our custom solvers utilized all CPU threads on a single machine. As you can see, the ECA SKIP solver achieved an average speedoff of 55%, significantly outperforming SKIP, while ACO SKIP took considerably longer to complete the task. While black box solvers cannot guarantee optimal solutions, the probability of finding one depends on several factors, including the solver's parameter settings, the algorithm used, and the specific nature of the problem. In our experiments, ECA SKIP found optimal solution in 100% of cases, where ACO SKIP did so in 92% of cases. The difference in reliability could be due to parameter settings, or it may indicate that the ACO algorithm is less suited for this particular problem of optimizing generation capacities. However, without further analysis, we cannot pinpoint the exact case. These graphs display the variable values obtained from optimizing generation capacity structure in a local grid. Specifically, they show the load on renewable energy systems over the course of a week, with colors representing different clusters of possible conditions. The graph on the left illustrates the summer season, while the one on the right represents the winter season. Here we have the weekly energy storage trends for the energy storage systems. The graph on the left represents the summer season, while the one on the right shows the winter season. These graphs illustrate how much energy is stored each hour, with the colors indicating different clusters of possible conditions. In our case study, we modeled a local grid with solar power plants, wind power plants, and energy storage systems over a 5-year forecast period using the mathematical model demonstrated earlier. Additionally, the system allowed for electricity to be bought or sold on the wholesale market. After solving the generation capacity optimization problem, the results presented in this and the previous slides were obtained. All computations were performed in a high-performance environment. We used a single node of 768 gigabytes of RAM and 2 AMD APYC processors offering 32 cores of parallel processing. The code was written in Julia, a high-performance programming language. Its solver was run 100 times, allowing us to calculate the average, minimum, and maximum execution times. In conclusion, enhancing the resilience of the local grid to military threats can be achieved through the distributed deployment of renewable energy sources and energy storage systems. However, planning such systems requires solving large-scale MILP problems efficiently. Our decomposition and parallelization strategies significantly improved the efficiency of optimizing the generation capacity structure in a local grid. The custom solver based on the evolutionary centers algorithm demonstrated the best performance in both speed and reliability. Moving forward, we plan to explore additional algorithms and assess the performance of parallelization in distributed memory systems. Thank you for your attention. That concludes our presentation. We will be happy to
Thank
take
you.
and discuss our findings further.
Thank you, Taras, for your presentation. Do you have any questions to Taras? No one. Thank you very much.
Thank you.